All right, and then it's all going to be added to 9. All right, 9 times the Laplace transformation of y to the first, which you just saw was y to the s. All right, and this is all on the left-hand side. So that's all on the left-hand side. So what does this all add up to be equal to? Well, it's going to be the Laplace transformation of 5t. So use your table and you can verify that the Laplace transformation of 5t is equal to 5 times the Laplace transformation of t, which is just going to be 1 over s squared. And so this is going to be 5 over s squared. Okay. So that's how everything comes together in a differential equation. When you know generally how to take the Laplace transformation of ordered derivatives generally, and also how to take Laplace transformations of functions, then you will be able to solve essentially any differential equation using Laplace transformations, which makes them very nice and generalizable. And it's also why they're so important in engineering primarily. Okay. So all that being said, if we were to group the terms together and reorder the equation, this is what we end up with on the left and right hand side. After you add everything up and collect like terms, you have s squared minus 10s plus 9 times capital Y of s, okay, plus s minus 12, all right, equals 5 over s squared, all right. So I can remove that, subtract, there we go. So now that we have this in place, we solve for y of s, all right. So this implies that capital Y of s is going to be set equal to the following. It's going to be 5 all divided by s squared times s minus 9, okay, times s minus 1, all right, plus 12 minus s, all divided by, again, s minus 9, multiplied by s minus 1, all right? Now that we have that, let me go ahead and make a few comments for you guys before we move on to the next video. At this point, it's convenient to recall just what we're trying to do. So we're trying to actually find the solution for little y of t, okay? We're trying to solve for y of t, okay? So we haven't finished yet. We still have to back transform. So we have to take our transformation with the Laplace transform and actually do an inverse Laplace transformation to get back the solution. And I'll show you how you guys to do that in a minute. It's no different than how you used the table previously to do a forward transform. You just use it again to do a backward transform. Okay. So we have to solve for the back transformation of the original equation, right, to that initial value problem. So what we've actually managed to find at this point is not the solution, but it's a Laplace transform. So in order to find the solution, all that we need to do is take the inverse transform like I said before. So before doing that, let's notice that in its present form, we will have to do partial fractions twice. However, if we combine the two terms up, we will only be doing partial fractions once. Okay? Not only that, but the denominator for the combined term will be identical to the denominator of the first term. And that's a nice fact. So this means that we are going to partial fraction up a term with that denominator no matter what. So we might as well make the numerator slightly what you call messier and then just partial fraction once. And I'll show you guys what all that means in the next video. So anyway, this is one of the things where we apparently are making the problem messier using partial fraction combination, but in the process we're going to save ourselves a fair amount of work. So be sure to review how to use partial fractions when you start solving some of these differential equations with Laplace transforms. It will save you quite a lot of work, and you can see how fractions and rational equations will become much more relevant for you guys going forward. So in the next video, I'll show you guys the partial fraction method, and then we'll jump right into solving the Laplace transformation by doing inverse Laplace transform to get back the equation that we're looking for. Stay tuned.